Okay, so let's go to the calculator and start entering second data. Oh, I have something there, so I need to clear. Second, clear the worksheet, and you're going to enter values in pairs. X will be this number, Y will be this number, and I'm going to recommend you enter as a decimal, okay? Because for the purposes of something I want to do, it needs to be entered as decimal. It doesn't really matter, to tell you the truth. You'll get the same results, but it's just something I want to do that if they're not entered as decimals, it'll be confusing. So we start 15.15, enter, scroll down, and now you put the Y value of the pair. Then you go for the second. Then you go for the third, 10.1, enter down, 0.2, enter down. Now we go for the fourth pair, 0.075 and 0.15. And the final pair. Okay, so work with that. I'll give you a minute. Check your work. Make sure it's always double as you read through. And I'm ready to go. Sorry. All right, are you ready for the next step? Okay, I'm going to start calling people. Make sure you're working on this. Sophia. Sophia. Oh, do I have my two Sophias? You entered as Sophia. Which Sophia is here? Sophia. Are you there? Can you hear me? Alejandra, you hear me? Maybe you can't talk. You should talk because this is your class time. So you should be able to speak. Sophia's not there. Okay. Yeah, you're there? Let's see who's here. Okay, I see Diego. Diego, do you have your hand up? Okay. I can't see everybody at the same time, so okay, there you go. So Diego, what do we do next? Denzel, what do I do next? I put all my data in. How do I get the results? How do I get the results from the calculator? We put everything into data. This one here. And now I'm going to hit second stat, and there are my results. What does LIN stand for? What does it mean?
That it's a linear, Jesus Christ, correlation, I guess you can say.
Well, we're going to get the linear estimates. That's what it's for, right? You're right. We're getting the linear estimates. So it's going to take a pair of data and try and correlate them linearly. Okay, there's other ways to do it if there's other pattern, but we see there's a linear pattern. So let's establish the equation of the line. That's what we're going to get out of this. So we're going to continue scrolling down for results. We begin with N. What is that?
Is that the number of values we entered?
It's the number of values. It's the sample size. It's the sample size.
Sample size.
And then what's this?
The mean.
That is the sample mean. Very good. That's Anthony. It's the sample mean. Okay. And then what is this?
Standard deviation.
Excellent. Is that Alejandra or Alondra?
Naturally.
Oh, sorry. I can't see.
Don't worry.
That's right. That's what did you say? You said it was what?
The standard deviation.
Which one?
The sample.
Right. So that's a
okay.
sample standard deviation, which is different from this one. What's this? Let's go back. So this one, we're all good until sample standard deviation.
That's the mean, right? Again,
No, this
Of
one's the
the-
mean. This is the sample mean or the average. This is the sample standard deviation. And the question is, what is that?
Isn't that the standard deviation of the population?
then
Excellent.
I think
Yes, it's the standard deviation of the population. Okay. So, which one is bigger?
The population one.
Check again.
The mean of the sample.
The standard deviation of the sample, then.
Yeah,
So
that's
I
standard deviation.
know what you meant. So
Yeah,
that
thank you.
sample, the standard deviation of the sample is bigger. It's because the fact is the only real difference between them is what you're dividing by. So let's look at these formulas now. Okay, so you need to be an expert in these formulas by next week. In fact, you should know all of these already, but we're going to go through them. This is the formula for the sample mean. It says sum all the values and divide by n. Whenever you see this symbol, you should think in your mind average. Statistics is about averages and relative measures, and you're going to see that in my demonstration today, okay? That is basically what statistics are. A statistic is a number computed from a sample. Here's a sample of data, in this case, 2 variables. We want to relate them. We begin with calculating average. Then we want to, this gives us an idea of what to expect. So that if we had to bet on what the next period would hold for the S&P 500, we'd be respected, I guess, for guessing that it would be 9.9% if this was these were the results in the past and things haven't really changed. You know, this is a range of circumstances have led to a range of values for the S&P 500, and we expect it to be roughly the same in the next period. That's what we would bet money on, that the next period would be 9.9%. But that doesn't tell the whole story, because there is a variation around here. There's a volatility, and we want to measure for that. And the measure for that is looking at how far, first we begin by looking how far each value is from the expected value and calculate something called, what do we call that?
That the variance.
Not just that, that's part of it, but what do we call that? It's a deviation from the mean. If you take each value here and subtract the mean, what do you get? So the logic is this. The mean, the sample mean gives us an idea of what to expect. It actually is the center of gravity of this data. It gives us, in other words, a value that is closest to all the other points. It sits right in the center in a balanced way. It balances the distribution from which this data is used. So if you calculate this value minus 9.9, put it here. This value minus 9.9, you put it here, and you fill this in. Do that for me right now, and I'll ask you to give me the values. What I'm interested in is a measure of the average deviation from the mean to talk about how spread out the values are, how volatile, how strange, how unusual. they are different, how different they are from the mean. I'm gonna call somebody to give me the values. Give you a minute. All right. Who's gonna give me the values? Just start telling me. Let's see who comes forward. What's the first one?
.051 is the first one.
Yeah,
The second one is .009. I'm still doing the rest.
okay, let me give it I'm just gonna write it as a percent because I want to make a point. So the first one is 5.1. The second one is, go ahead, Denzel.
It was .009, but in percent like 0.9.
Okay. But a negative, right? Don't forget
Yes,
the
exactly.
sign is very important right now. And then 0.1. And then
Negative 2.4.
negative 2.4. Okay. And
Negative 1.9. Yeah, 1.9.
negative 1.9.
0.9.
Okay, so here we have what are the deviations from the mean. Why don't we just average the deviation from the mean? Why don't you find for me the average of these? Add them up and divide by 5, or use your calculator the way I just taught you to put them into stat mode and get the mean for me. Tell me what you get. So if I did this,
It's giving me 0. I don't know why.
yeah, why is it giving you 0? Try it again. So if I put it here, I'm going to overwrite what I did before. I'll put it back later. But just to show you, we can do the mean in here to make sure we make no mistakes. So second data, clear the work, and then I start entering. Now, when I enter the data, I can enter it as 5.1 or 0.51 to make my point. Enter down, and I skip Y and go right to X. Oh, no, that's wrong. Wait. No. Okay, skip Y and then put in 0.9 negative. Enter down, skip Y, 0.1, enter down, 2.4 negative, no, not there. Gee, been out in 4, 2.4, negative, enter down, skip Y. So I just want to do one variable statistics, not two. So this calculator can do two. And then 1.9 negative, enter down, down. And so now I ask for second stat and I just get the mean. Oh, I got 0 too. How many of you got 0? Yeah? You want to put in the chat if you don't want to show me? Alondra got it. So does that make sense? Why
That's
is
the same
it 0?
number I got, yeah.
Why will it be 0? Will it always be 0 for any pair of data? The answer is yes. The deviation from the mean calculated like this will always be 0 because what we're doing is considering every value that makes the distribution. Remember, distributions, if you don't, go back and watch my video on review of statistics. The mean is the balancing point, so it'll be here. So even if you had a skewed distribution that was like this one, the mean would be balancing the tail side and the other side in a way that this area is equal to this area here, okay? As a result, the deviation from the mean, which is calculated as x minus x bar, takes each value over here and subtracts the mean. So all deviations from the mean will be negative on this side. All the values below x bar will be negative deviations from the mean. And all the values above will be what? So if I take a value higher than x and I subtract x bar, so if I take a value higher than x bar and I subtract x bar, what will I get? A positive or a negative? Okay, there you guys are. I see you in the chat. Positive. You get a positive. And you know what? The positive differences here will cancel perfectly with the negative differences here. Not by number, but in total. That is why x bar is a balancing point, because we're balancing the deviations on this side from the deviations on that side. So the very way that we're doing this, unfortunately, does not allow us to sum and divide by 5. We can't do it. The problem, what is the problem? The problem is the signs. So what we're going to do instead is get rid of the signs. One way to eliminate the signs and only care about the size of the deviation, not the direction, is to ignore them. But statistics did not take that route. Instead, they did something else. What did they do to get rid of the negative? To calculate a measure of spread or volatility. What did the statisticians decide to do to get rid of the negative? Uh-huh. Nashali, that's you?
Yes.
They square it. They square it. They square the values to get rid of the negative. So I want you now to square each value in this column. And I want to talk about that after we do that. And then we're going to go into the formulas to repeat what I just said in a more general way. So square each one and tell me what you get. You can write it in the chat so I know you're paying attention. If you're not on camera, you can write it in the chat. I mean, it's not a substitute, but shows me you're doing something there. Okay, what'd you get? I'm gonna ask everyone to say something. Alondra already spoke up. Nashali many times. I see Elizabeth is there. Denzel already spoke. Let's see who else has to talk to me. Joash, what are the values here? He's not there. Diego is saving everybody. 2601. Okay. So 26.01. 0.81. 0.01. 0. No, that's not 0. It's 5. 5.76. Anyone dispute these numbers? So these are the square values of this. Does everyone agree with the numbers first? So I have a very good question for you. The question is, I want to see your answer in the chat. What are the units associated with these values that were computed? 26.01 what? Here it was 5.1%, but what is this? 26.01. Alondra says percent. What does everybody else think?
Iberia 3 con destino Roma, Emici, ¿no? Puerta HKT3. E Iberia 3858 con destino Lanzarote, Puerto M35.
Javier, are you there?
Para el resto de vuelos podrán comprobar cuál es la puerta de emergencia.
Turn off your mic unless you want to talk to me, which I'm fine with, but you have background noise. BPs, Diego, what's BPs? Oh, basis points. Nope. So when you square a value, you also square its units. So for example, when you take 5 centimeters times 5 centimeters, what do you get? 25 centimeter square. So these are really percent square. What does it mean? We don't use that. We don't interpret that. We do not even talk about that. So that's what we're going to do in our calculation of the average deviation from the mean. We're not going to talk about it. What we're going to do instead is we're going to average these values, summing them and averaging them. Here's the formula that you may have seen, you should have seen for standard deviation. This is what we did. We squared the deviations from the mean, and I'm suggesting we have to average them, just like we did over here, but we use one less. One less doesn't matter if, let's say, you have 1,000 observations, minus one less, it's not going to make much of a difference. But what it does do is make the number in here a little bit larger than if you divide by n, because you're dividing by a smaller number. This helps you account for the spread of the values, okay? And in terms of statistical theory, This is known as an unbiased estimator of the true standard deviation. Remember, this is just the sample. These are all sample formulas. Sample statistics are all in this list because my data was a sample. So we have a name for this where you average the square deviations from the mean. What is the name of this? The name is over here. What is the name of this?
Variance.
It is the variance, but not just the variance, it is the sample variance. Okay, it's the sample variance because if it was the true variance, we would divide by n, not n minus 1. And also this would not be x bar, it would be the true mean. All right, so then what we have to do, because we've taken the average of the square deviations from the mean, we have to go back to the units of percent, so we take a square root. That's why we take the square root here. I explain why we square, and I explain why we take the square root, and it all has to do with the mean as the center of gravity, the expected value of the distribution of data. The mean is the point closest to all other values, or the value closest to all the other points. All right, so we have mean standard deviation. And then I want to talk again about my graph that I made. So I'm going to talk about the direction. So we said the direction here is positive. So what does it mean to be positive? I'm going to clean this up a little bit here. I'm going to take all, I'm just going to draw this again. How about that? And it's not going to be a great, perfect drawing, but it's going to be like whatever it was. I think it was steeper. Yeah. There was one in between here, I think. Okay, so this was like the data, right, that we had. And that's not right. I had 10 and 20. No, that's not good. I'm going to go back. Hold on. Let me go back to my drawing, because I don't want to throw it off. Lost it. Let me just erase this and this. All right, so here's my data. And my question was about the direction. So we say it's positive. What does it mean? What's another way to understand positive? Well, I'm going to divide the data by the expected value, which was the mean. And the mean was like 9.9, right? That's what we got for X. And for Y, what's the mean for Y? We never even got that far. Let's go back to the, let's see. If I keep going. Okay, I didn't put Y in here. So I got to go back to my data. I have to clean it and put the data back in. Can you guys tell me what Y, the mean of Y was? I want to put it back. For people who are still working on this. You're going to make a lot of stats calculations, so get used to it because that's what we're going to do for the next 6 weeks. Okay, so that's the X results first and then the Y. So 17.8 is the mean for Y. So around 20, which is about here, you have the mean for Y. Okay, my drawing's badly not to scale, but I'll be able to make my point with it. My drawing isn't great, I admit it. So I've divided the data with X bar, Y bar, and now I've divided it in half in a way to say, these are high values of X, these are low values of X, these are high values of Y above X bar, these are low values of Y below X bar, Y bar. What did I just say? These are high. I'm very distracted. Can you guys, if you're going to be in the camera, pay attention. I don't know where you're looking. The high values of Y above it, Y bar, low values of Y below Y bar. When X is above its mean, where does Y show up? Where are the pairs of data? Where do they show up? Do they show up above the mean of Y or below the mean of Y?
When above,
When X is high, Y is high. What about when X is below the
the
mean of X?
opposite.
Where does Y end up? Below the mean of Y or above the mean of Y when X is below? Alondra tells us it's lower. So we have a pattern. This is our pattern, and it describes a positive pattern. When X is high, Y is also high. But also, when X is low, what do we find about Y? When X is low, where's Y? Y is low. What does it mean? It means that X is reinforced by Y. Whatever X does in relation to its relative measure, Y does the same. That's a positive relationship. If X is low, Y is low. If X is high, Y is high. How do I define high and low? Relative to their means. So what about let's put this here. How do you describe this relationship?
Proportionally linear.
Say it again.
Proportionately linear.
It's linear. What is the direction?
Negative.
So this is a negative. Is it strong or weak?
Strong.
It's strong, or you can say perfect. Negative linear relationship. So the perfection of it refers to it being on the line, reliable, no volatility, just like here. The negative refers to the trend. Let's divide it like we did the last one and talk about the pattern. So I don't have any numbers, but this is like X bar. And just looking at it, this is the balancing point of the data, y bar. And what do I say? What happens when x is high? When x is high, where is y? High or low?
High.
When x is high, where's
Yeah,
y?
when X is high, Y is low.
Very good. So when x is high, y is low. When x is low, y is?
High.
Ah, very good. Denzel's got it. Y is high. So relatively speaking, we've divided the data in half, and it's a clear pattern. When x is high, y is low. X is low, y is high. It's opposite. When it's opposite, it's called a negative relationship. And I'm going to show you in a second why we call it negative. Again, you have to be an expert at this. You guys should be able to make this presentation next week. And so let's talk now. So that's the direction, all about the direction. Let's look now. Let's look back. Before I continue, I'm going to go back to the formulas and talk about this covariance. The covariance is a measure. It's not just a graph, because I showed you graphically. Let's get a number. Let's get a measure of direction. And that was the covariance will give us. It will give us the direction of the relationship. Oops. What happened here? What does it look like? So every time you see a formula, try and connect it to what you saw before. Again, just like we did for unit 1 and 2. If you connect them, you're memorizing less and you're understanding more the formulas related to each other. What does this look like? What do you see? What do we call this when we see this? What did I tell you? What is it here when I told you it was here or here? These are the symbols to show you're averaging, okay? You're getting an average. You're getting an average of what? Okay, let's see. Go back here for a second and let's look at this a little bit. Can I write this? Oops, I'm going to leave out the square root. Can I write this like sorry. This formula here can be written like this. The variance can be written like this. Does everybody agree? The variance, what sign will the variance be? What will be the sign of the variance? Positive or negative? Diego says positive. Why? How do you know it's positive? Because it's squared. Because it's squared, it will always be positive. So variance can be only positive, but covariance can be positive or negative. Okay, so all I'm doing here is changing one of the factors. I'm finding the joint relationship between X and Y. What does that accomplish when I do it? Well, think about what we just talked about. Remember this here. I'm going to take this with me. Back to the graphs. So when x is high, y is low. No, let's do it here. When x is high, what will this be? A positive or negative when x is high? So when a value of x is below x bar and you subtract the x bar, what will you get? A positive or negative? If you guys don't participate, I am going to leave you guys to watch videos on your own. And I understand people don't like that, but I'm not going to talk to myself. I have videos already with all this material. You need to participate. Alondra says it's going to be positive. And she is right. So this will be positive. So this will be positive. So I'll put this here, x I, x bar, y, I, y bar. And if y is high, what will y, I minus y bar be? Positive or negative? No. If x is high, it's going to be positive when I subtract it by x bar. If y is high, it means it's going to be positive if I subtract it by y bar. Positive times positive. What's a positive times a positive? Positive. Okay, now let's do the next one. What if x is below x bar? What will this factor be, positive or negative? Negative, Diego tells us. And then if y is below y bar, what will this factor be? Carlos tells us. Negative. What's a negative times a negative? Positive. So what you're doing when you have this kind of a shape where this trend appears, the covariance will be positive because you're averaging a bunch of positives. So that's what the positive refers to, right? Now let's do it over here, where we have what I so-called a negative relationship. Let's see. You guys getting this? Just explaining the formulas because I don't want to talk about it again, but you need to know this. You need to be experts. Really experts. So when x is high above its mean, what will this be? Positive or negative? Positive. And when y is low, y minus y bar will be negative. And what's a positive times a negative? Negative. Good. When x is low, it means that the deviation from the mean will be negative. When y is high, the deviation from the mean will be positive. That will result in a negative, and that's why you have a negative relationship, because you're going to be averaging mostly negative values. So the result will be negative. Got it? So that's how it works. That is a covariance. Now the covariance gives us the direction. So the covariance for this will be what? Positive or negative in this graph? What did we already say? Covariance will be greater than 0. What will the covariance be in this graph? Positive or negative? Very good. So the covariance will be negative here. It will be positive there. And now let's look at this one. That's moderate relationship. What will the covariance be here? In this one, Denzel, that's scattered around. Is the covariance positive? Is the direction positive? Yes, the covariance will be positive. And what about if it goes like, oh, no, I want to do red dots. Hold on. Going to make, what just happened? Make red dots. What about the covariance here? Will it be positive or negative? Okay, it'll be negative. All right, so we need another measure because covariance is not enough.
Excuse me, Professor.
Yeah,
Is covariance always tied to the direction of the graph?
exactly. The sign of the covariance, the sign.
Exactly.
Right. So we have
Oh.
a problem though, because there's something different, even though these both have a negative covariance. How do we know that this one above is perfect and this one below is not perfect without seeing the graph? We need a number, we need a measure that tells us about the perfection. That measure is called what? So we have another formula for that. Covariance tells us direction. It's the covariance. It's not the variance, it's the covariance, but it's very similar, right? If we take the covariance sign, we know the direction, but the value of the covariance is hard to interpret. There's no standard way to interpret a covariance number. What we do to make it a standard way is to standardize it. In other words, we take the covariance and divide it by the two standard deviations to get this. What do we call this? Correlation coefficient. It's in the list. Okay, this is the correlation coefficient. Right, Londra, Alejandra, thank you. This is the correlation or the correlation coefficient. And it gives us an index, the standardized covariance that tells us the strength. This tells us the strength of that linear relationship. And it tells us the strength of a linear relationship between two quantitative variables. It's easy in finance. Usually we have quantitative variables. However, if you're interested in trying to get a correlation between something like the gender of a CEO and the market cap of a firm, you can't do a correlation for that. There are other measures that you can look at, but you can't do this correlation because correlation has to be with quantitative data. Quantitative data is easily finance data, financial data like returns are quantitative, okay, not categorical data. So what we get when we standardize always is R, an index, and the index is always going to be in between -1 and 1. So now you guys know this probably. Let's go back to the graphs and we're going to put kind of like an estimate of what we think R is. Not an estimate, like a, an idea of what R should be given the different graphs, because you know what an R of -1 is and an R of 1 is. All right, so which one is an R of +1? I should put numbers on these. So let's see. I started here. Then I did this. Then I did this. And then I did this. All right, so which one has an R of +1? Right, Diego says number 1. So R is equal to +1 here because it's perfect. It's strength. It's the strongest relationship. Which one has an R of -1? Very good. 3. So 3 is also perfect, Alondra, but it's a negative direction. So the sign again, the sign of R and the sign of covariance are going to be the same. All right. And I'm going to show you exactly why. But right now, you guys trust me, this is perfect, but it's negative. R is -1. What about in number 2? What would you say the R is for number 2? With some idea. Okay, Diego says 0.5. Do you think it's a little stronger though, Diego? I think it's a little stronger. I mean, it depends. My scale isn't the greatest to judge. I'm going to say it's 0.8. I'll say 0.8 just because they're pretty close. They're not so scattered. The trend is clear. So it's a positive 0.8. And then down here, I'll make it more scattered in this one. I'll make it more scattered, but trending down. What would you say about 4? Now we can use your 0.5, Diego. Yeah, Alondra. So we can say R is negative. Don't forget the negative. And then something like 0.5 or 0.6, something like that. I think 0.5 is fair. I could say 0.5. Okay, so it's closer to 0, but it's negative in that case. What does it look like? When is the R 0? What does it look like? Draw something for yourself where R is 0. See if we get the same thing. What's that? Oh, okay, yeah, that's right, Diego. You guys are funny. It's going to be like, oops, let's make no trend, just flat, like Diego's showing, like flat, random, flat data, no trend, R is 0. Something messy, yeah, scattered everywhere. So these are all scatter plots, okay? That's what we've made. I erased it, I think, at some point. These are scatter plots. Always plot your data before you analyze it. Okay, so you guys then, now if you want, you can take a screenshot of that. I have this in the notes in the videos too. So you can look at that as well if you want a record. I'm going to post this video up too. If you didn't get a screenshot now, you can get it after. All right, so the next question is, how do I know R and covariance always have the same sign? How do I know R and covariance always have the same sign? Who told me that the standard deviation, the variance and the standard deviation will always be positive, right? This will always be positive because it's squared. So the standard deviation will always be positive. Not true for the covariance. The covariance can be negative. Because of that, you cannot take the square root of the covariance, right? Covariance can be positive, covariance can be negative. Can be 0. Okay, covariance can be all of those things. There's no restriction. Actually, I shouldn't write it because it's confusing. It can be anything. It doesn't have to be positive. For that reason, you cannot take the square root. That's what I will write down. Cannot take square root. Because it can be negative. So the reason why R is the same sign as covariance is because these will both be positive. So R and covariance have the same sign. These are different formulas for coefficient that I use for illustration purposes, but essentially it's the standardized covariance. That's what you can think about it. reducing it to an index is no longer a percentage. It's an index between -1 and 1, and it tells us the strength of the linear relationship between two quantitative variables. If you do not have quantitative variables, you cannot interpret this. If you do not have a linear relationship, you cannot interpret this. Okay, you have to have some sort of trend. And finally, we're going to talk about this. What is this? B. This is the slope. This is the slope of the relationship, which we got out of the calculator, and we got it by looking at the data. What was the slope? What we found from the calculator is that the relationship can be estimated by a line that has this equation. So y equals, A was 0, if you remember. So this is the equation of the best fit line as per your calculator. Best fit or prediction line. Or least squares, regression line. There's different names for it. And I put a hat on. Why do I put a hat here? I put a hat here because it's not representing all the points in general. In general, even though I have like this line that estimates the relationship, it doesn't fit all the points. Okay, it's just a prediction line. It doesn't represent all the points. If it was a mathematical line, then sure. In this case, okay, we have the mathematical line predicting that because it's a perfect positive relationship. The problem is it's still not a mathematical line because it doesn't go through infinity, negative infinity. It can't go like that. This line, the prediction line between these points, only exists around the range of values, only about here, okay? And there's some rules about looking at things, but how far you can go. But in general, you don't extrapolate beyond. You don't use the line too far outside the range. It's not advisable because relationships can change outside the range. So we prefer that our data are close to the line. We like to have an R that's high to make predictions. If you have, if you like a slope of 2, then you should use that to make your predictions or your decisions based on whether the relationship is strong. Okay, so you need all these numbers, all these things that we just calculated, you need them all to make a decision. We are at our time, so I am going to let you go, but I want you to read this, okay? If you didn't understand half of what I said or 3/4 of what I said, watch the statistics review to be ready for next week. Like I said, I expect you to be an expert of this page by next class. So this is the first part with historical, or what I call ex post data, where every data point gives you equal or equal value information. So I just average them. I give them equal weight. Well, in ex ante data, what I have are 2 things. I have basically the population described as a distribution with 3 possible outcomes. I do it this way because I avoid calculus. In fact, I should be giving you a function that represents the distribution, but I avoid that because I can't assume you guys learned calculus to some efficiency, but I give you 3 possible outcomes, and we manipulate this to do the same calculations. Mean as the weighted mean, variance and standard deviation as the weighted standard deviation, the correlation, the covariance, sorry, the correlation and the slope. They're all Greek letters because what I have that I'm looking at represents all possible outcomes. In other words, population level data. So I use Greek letters. So what I want you to do, I know you're going to have your break. I want you to spend some time looking at this, familiarizing yourself, and I'm going to show you the best way I know how. I mean, the notes are on the platform of how to calculate this manually, but although ex post can all be done in the calculator, this has to be done manually. All right, so do some practice with that before we meet on Tuesday. I'm going to talk about this a little bit, and we're going to jump into the notes in Unit 5 on Tuesday next week. We will be virtual until the 12th because I'm not in Puerto Rico for 2 more weeks. And then we will be back in the classroom, and we will finish on time if we keep with the schedule. So we're working towards the April 26th test and the final exam the following week. So every class we meet, we're preparing for the final exam, okay? We'll get you there. I'm going to put this video on the platform. I recommend that in the future that you guys are participating in the classroom. I guess, some of you are home right now because of the holiday, but you guys should figure out where you're going to sit and observe the class and participate in the class, because it's not a good time to be falling behind. This material is very quantitative, the most quantitative. Well, I don't know, compare it to Unit 1 and 2. But it's a lot of statistics that was not in Unit 1 and 2. All right, so have a good holiday. Happy Easter.
You too, ciao.
Ciao, thank
Cool,
you.
Professor. Goodbye.
Bye.